Okay, we start again with Sergio Pastor. We have the pleasure to have him with us, and he will talk about the number of neutrinos in non-standard scenarios. Thank you very much.
Thank you very much for the invitation, Cristina, Francesco, and Olga. I guess Olga will be here next week. So my talk will be somehow similar to what Stefano discussed before, and a bit different also, otherwise just like a repetition. No. So my idea is to show you some cases where we can change this parameter, the effective number of neutrinos, in non-standard scenarios. Actually, when I say non-standard scenarios, I will focus on non-standard neutrino scenarios, when the change on this parameter and effective is coming from the neutrinos and not from additional relativistic particles. Okay, so you've seen this picture before, or a version of this picture, the evolution of the universe. And as you know, the evolution of the universe depends on the particles that are in the universe, the components. So the energy density of each of the different components evolves with the expansion, so the scale factor A, in a different way. And as you know, we have radiation, relativistic particles, matter, non-relativistic particles, and eventually dark energy as a cosmological constant or as a more complicated case. So here, I'm actually showing the evolution of the energy densities of the different components in the universe with time from an initial temperature of the order of 1 MeV or so, and measure in this so-called omega factor that, as you know, is just a way to show the energy densities in terms of the critical density of the universe, so that at each moment, the sum of the omega factors of the different components is always 1. So what is important for this talk is that at the beginning is the relativistic particles that rule the universe. I think this was already said yesterday. So the same neutrinos and photons that are almost irrelevant now were ruling the universe, like you see here, more or less 60-40. So if you have a way to enhance or to reduce the contribution of relativistic particles to the universe, this radiation dominating period will be longer, shorter, and will also modify the so-called equality time, the onset of the matter dominating, and so on. What is interesting from this point is that the neutrinos are the only known particles that have this transition from relativistic to non-relativistic particles. If they are always relativistic, their evolution will be, as you see, always parallel to the one of photons. So we just add a mass to the neutrinos, and you see the transition from relativistic to non-relativistic particles and how much they contribute to the energy density today, which is essentially 2% for a 1 eV neutrino. Okay, again, evolution of the universe. I'm focusing on the period of neutrino decoupling, as Stefano was discussing before. So neutrinos are interacting with other particles, electrons, positrons, and other neutrinos up to a second or so in the history of the universe, energies of the order MeV, and just before primordial nucleosynthesis. This is just a zoom of the same period, where you can see that and I like always that the expansion of the universe is going to the right, okay? And this is not always the case with the plots. And or Stefano showed the one by Pablo, and it's just the opposite. Okay, anyway, so large temperatures, 10 MeV up to also 1 MeV, neutrinos are coupled, neutrinos are interacting, so they have the spectrum of a relativistic fermion that you can see here. Then they will no longer interact through weak interactions, so in collisions will become less and less important. They decouple, and they form the cosmic neutrino background, which is the same form of a relativistic fermion, except that with a temperature which is the one of neutrinos, is different from the one from photons by the corresponding factor that you know well, due to the annihilations of electrons and positrons into photons, but not into neutrinos. Okay, so just after electrons and positrons have essentially disappeared, the radiation content of the universe in the standard universe is photons, neutrinos. Since we are measuring photons, we just normalize to the photon energy density. And with the corresponding factor, we have this. And this 3 here is the number of neutrinos. Okay? This equation, as Stefano showed, is valid in the so-called instantaneous decoupling approximation, where the neutrinos do not get any entropy transfer from the electrons and positrons. But as you can see, these two phases are very close, and this will lead to this 0.0 for something that Stefano was discussing. Okay, now instead of a 3 here, we can generalize and say, okay, anything that looks like radiation at this period, I will put it in this way. Okay, so measure the contribution of other relativistic particles in terms of a neutrino. Okay? A neutrino which behaves in the standard way, which in this is the effective number of neutrinos, or effective number of relativistic neutrino species, or maybe we can say radiation content. Okay, I was in a school 2 couples, and all the students were asking. I can use the micro. No, now it works. Yeah, okay. So the students were asking why it is called neutrino if it can be other particles. And yes, this is just a historical thing, okay? Back 50 years ago, this was the way to measure the number of neutrinos. There was no other way. When finally the number of active neutrinos was measured with accelerator, so this just became, as many other cases in physics, a historical name, okay? So we still say an effective number of neutrinos. Okay. This parameter has been measured from cosmological observation, and that's also what Stefano was showing, or it was shown by Maria yesterday, okay? Now, at the beginning of this century, actually with CMD data, we could have a lot of radiation in the early universe, up to 17 in neutrino terms, okay? This was very fun for everybody working on, early universe dynamics. Still, just a few years later, this was significantly reduced to something like 4 plus minus 1 neutrino, 1 point. And as was shown before, now we don't have much room, okay? This number could be anywhere. And it's a bit sad that it's around 3. Well, it's sad for those that are working on this. For the standard case, it's okay, it's just 3. Okay, so this is the value by Planck, which has not been really different. It's not really different from including the DAISY data, because this is 68. It has just moved a little bit, the best fit, but it's just 3 plus minus 1/3 of neutrinos at 95%. Okay, so there's not much room to additional particles. Now, how can I change the effective number of neutrinos? I can, of course, add additional relativistic particles which are not neutrinos. Okay, scalars, pseudoscalars, decay product of heavy particles, anything. Okay, this is not the subject of my talk, but I'd like to show this plot. Okay, this plot is fantastic. It's from the Planck paper, except I told you that time is going from right to left. So this shows you in the bottom that if you have a particle that was present in the early universe and in equilibrium with the rest of the plasma, depending on when this particle decouples, how much this contributes to the effective number of neutrinos. Okay. If this particle is a fermion like a neutrino and decouples around neutrino decoupling era, of course, counts as 1. If this particle instead were always coupled to photons and electrons through the whole electron-positron annihilation, it will not count as 1. It will count as more than 3, actually. Okay. Still, if we go back to early phases, you see that the contribution is less and less important. Okay, and we go down to these numbers, which are more or less probably the future sensitivities on an effective. Okay, so proving with good precision the value of an effective, we can actually prove the existence of relativistic particles that decouple in the very early universe. Okay, that's clear. Instead, in my talk, I will concentrate on non-standard neutrino physics. Okay, so there are no additional particles that are not neutrino or neutrino-like. Okay, so how can we change the effective number of neutrinos? So I will discuss 2 cases, the case with non-standard interactions of neutrinos with electrons. I will also discuss the case of an additional sterile neutrino which is mixed with the other neutrinos, but there are other cases what are not showing in this talk. For instance, we can consider primordial neutrino symmetries. There has been a lot of work on that, and I think the last one is by Julian, very interesting, because you can actually change the effective number of neutrinos if you have an asymmetry. Okay, so the effective number of neutrinos will not be 3 in this case. It's quite interesting. The other case that we consider recently is when You have a mixing matrix of the three neutrinos, which is non-unitarity, thinking it mixing with other heavy states. Okay? So again, let me emphasize, these are cases where you don't have additional relativistic particles, you have your neutrinos, but in non-standard cases. Okay? Actually, even in the standard case Stefano was discussing, the effective number of neutrinos is not 3, it's just this. Okay? And actually, I'm just curious, how many people in this audience were involved in any of these 2 papers? 5 people, interesting. Okay, so you see how a lot of people care about this very small change, okay? Also because it's fun, it's fun and complicated, actually. Good, standard case is this. Now we go to other cases. Now I consider this case non-standard interactions of neutrinos with electrons. So as you know, in many particle physics models where neutrinos get a mass, there are also extra interactions of neutrinos with other particles. It can be quarks, it can be other charged leptons. But for the decoupling of neutrinos, only this kind of interaction matter. The ones that relate neutrinos with electrons, because quarks essentially were not there in the early universe. So you have the Lagrangian of the standard model, and you have this additional term coming from non-standard interactions, which is parameterized by these epsilon parameters, okay? And there are 2 different epsilon parameters. The ones that are so-called non-universal, okay, because they link same flavor of the neutrinos, so they change how the neutrinos talk to other neutrinos of the same flavor in the standard model. The ones that are flavor changed, which are always 0 in the standard case. Okay. So what we are going to consider is if this interaction exists, how they will affect the neutrino decoupling in the early universe. And back to the same plot, if the thermal contact with electrons and positrons is modified, if you have a longer contact, you remain coupled to electrons and positrons with a longer time, so you will share some of the entropy release, the number of neutrinos will be enhanced, or in some particular cases, the values of these epsilon parameters can reduce a little bit the contact of neutrinos with electrons and positrons. Okay, so again, the same, we were considering the evolution of the neutrinos in the universe with the same code that Stefano was discussing, in this case with only 3 neutrinos, but including the effect of a non-standard interaction, which affect not only the collision integral, but also the matter potential term. Okay, this is one example when I consider only one case, epsilon parameter, linking the nu e with nu tau. Okay, this is a flavor changing, so in the standard case is 0. So the minimum is actually for 0. In this case, we recover the 3.044 standard case. So if this value is enhanced, positive, negative, it doesn't matter. You see that neutrinos will be longer in contact with electrons and positrons, and the effective number of neutrinos is larger. Okay, of course, larger means up to double the standard case, but this box here are the values of the epsilon parameter which are okay with laboratory constraints, okay? So it's not that you can actually change much the effective number of neutrinos with epsilons that are still okay with laboratory measurements, okay? It's true that you enhance a little bit, but not much. Now, let me show you instead the case of diagonal parameters. So in this case, it's a bit more interesting. Let's look, for instance, at this. This is the EE. Standard case, again, is 3.044. If I go to positive values, I enhance the effective number of neutrinos. If I go to negative values, I reduce a little bit the effective number of neutrinos. It's never below 3. It cannot be below 3. But it's, instead of 0.04, it can be down to 0.03. Still, you see the boxes. It's not that you can deviate much from the standard case. Okay, all these bounds of the epsilon parameters are also calculated taking into account only one parameter each time. So what we have considered is when you have more than one parameter present in the early universe. So instead of this kind of plots, we have these contour plots. Okay, this is one example. Again, this is EE, non-universal, and this is flavor changes. Okay, 0, 0, we recover the standard case. And if we go to larger values, you see that you can see 3.07, 0.8 there. Instead, if we go in this direction, we just reduce a little bit the effective number of neutrinos. Okay, this is one example. This is another one. Okay, so the conclusion from this part is that you actually change the effective number of neutrinos only with neutrinos, with extra interactions, but not that much. Okay, still with this promising of future sensitivities on the N effective of the order of this, okay, maybe something we could eventually measure. Okay, good. This was one example. And this is the second one, which is probably better known, where instead of 3 neutrinos, I have 4 neutrino states. The fourth one is heavier and sterile. And in principle, is introduced to explain some of the anomalies in experimental data that we saw yesterday. Okay, now we have, instead of a 3x3 mixing matrix, we have a 4x4 mixing matrix. New elements here, and we have 3 additional mixing angles, as you can see here. 1, 4, 2, 4, 3, 4. Okay. This is the so-called 3+1 case, where you have a heavier neutrino state. If I go to the early universe, I check whether through mixing this new state is brought into equilibrium or not. And this, as it was discussed previously, depends on these values, on the mixing parameters, and also on the delta m square. Okay, let me remind you. Yes. Yes. Okay, but actually can be calculated for any value. But it's, yes, it's larger than any of the other 3. Okay, so what Stefano was showing this plot comparing the, let's say, oscillation terms with the matter potential. Okay, which is funny in the early universe is that the oscillating term is not constant; it's growing because the universe is expanding, and the other terms are like falling. Okay, again, I go back to this plot, and okay, well, if I produce my sterile neutrinos after neutrino decoupling, okay, there will be some oscillations. The nu's, nu mu, nu taus will be converted into nu s, but I cannot produce extra neutrinos because neutrinos are already decoupled. Okay, the effective number of neutrinos will be 3. We will have maybe huge distortions on the electron neutrino state. It will affect, for instance, nucleosynthesis, but I cannot alter the value of the effective number of neutrinos. If instead the oscillations are effective before neutrino decoupling, yes, the additional species, neutrino species, can be brought into equilibrium, and then eventually we will have an effective equal 4. Okay, and of course there is some cases where we are not at 3, we are not at 4, we are at 3 point whatever. Okay, so this has been studied in many papers before. For instance, this is the case where instead of the 3+1, we have the 1+1. Okay, in this case, you only have 1 delta m square. Okay, this is EV square, so EV will be around here, and just 1 mixing angles. Okay, and this is quite easy to see because we have these lines, okay, of equal value of the final effective number of neutrinos. This is the extra one, so it can go from 0 to 1. Okay, for this region here, the mass is too small or the mixing is too small, so sterile neutrino production occurs after decoupling, and effective is 3. Here instead, the production is effective before neutrino decoupling, so the final value is 4. And all these cases are in between, okay? If you want to solve some of the anomalies, the point is that you need something like here. So it is very difficult to prevent these neutrinos from being brought into equilibrium, and effective is 4. And this is not what we see from CMB and other cosmologic, unfortunately. Okay? As I told you, this is 1+1. So what we did, yes, is to, again, use a modified version of fortepiano, but instead of for 3 neutrinos, we use 4 neutrinos. And we can use not only 4 neutrinos, we can use as many mixing angles as we want. So we included the 3 different mixing angles between active and sterile neutrinos. Okay. And you can calculate things like this. This is the evolution of the energy densities of the different particles that are relativistic and later become non-relativistic or fully relativistic for one particular case. Only one mixing angle is 0 in this case. Okay, total radiation. Okay, this is co-moving, sorry, this is co-moving energy density. Means that if you have only relativistic particles, this will be constant. If you have massive particles that annihilate, this will increase. And this is actually what happens here and there. And the point is that here, muons and antimuons annihilate, and you have enhancement, and here is electrons and positons. And in this particular case, the sterile neutrino production is around here. So an effective finally is 4. Okay, so this is one of the results where only one mixing parameters active sterile is non-zero. The other two are 0. Well, it's not surprising that you recover something similar that I was showing you before. Okay, efficient production before decoupling and effective equal 4. Production after decoupling and effective equal 3. Intermediate cases, and again, for the anomalies, and effective is equal 4. So what was new from this analysis is that we can actually use more than one mixing angle. And it is not surprising that it goes in the way that the production of sterile neutrinos is more efficient. For instance, this is only one sterile mixing. This is with 2, and this is with 3, okay? So the more mixing that I add, the more efficient is the production, and at the end, you have inequal 4 for a whole region here. Okay, good. Okay, another way to see this is with this ternary plot that we somehow invented, where you have the mixing parameters, this one, this one, this one, okay? I think that they sum up the extent to minus, I don't remember. The logarithm sum up to minus 13, I think it was, okay? Okay, it doesn't matter. For this case, and for this value of delta m squared, which is small, okay, compared with the anomalies, you see that small values of the all mixing parameters, you have 3. Big values for any of these 3 mixing angles, you recover for here, there, and there. Instead of this value, you go to 1 EV squared, you see that the region where N effective is 4 is larger, okay? Either there, there, there. It is not completely symmetric on the, okay, but it looks like that, okay? The symmetry will be, I think, just there, and it's the green triangle, okay. This is the symmetric, okay. So it's a bit distorted, okay. Okay, so this is just to show you that it's very difficult to prevent these neutrinos, if they exist with these mixing parameters, to be there in the early universe, okay? This is what you expect N effective equal 4, and this is not what we see, okay? So it is very difficult to go, to have a sterile case and go below 4, or in the standard case with 3 neutrinos to go below 3, okay? Nicola will show you some, like let's say, very bizarre model with very low reheating temperatures. What they did, okay? So actually I'm done. Sorry. Well, not sorry. Okay, you are happy actually. So these are more or less the conclusions. So what I wanted to show you some cases where the effective number of neutrinos is changed only with neutrinos. One case is non-standard neutrino-electron interactions. You do change the effective number of neutrinos, but only to very small enhancements, as you can see here. And the other is the well-known case of a fourth sterile neutrino mixed with the other state, where it can change the effective number of neutrinos. And what I didn't discuss, and it is linked to the Maria's talk, is that you have also the effect of the mass. Okay, and this gives you another bound, and it's actually not really improving the situation as far as I know. Okay, thank you.
Okay, yeah, time for questions. Please, Georgia. Yes.
Yes, very nice talk. Thank you. In one of your earlier slides, you showed the equation of how you introduce the additional sterile neutrinos in F3+1, and I think there was a matter potential or something. term.
This one?
Yeah.
Yes.
So what happens if you introduce non-standard interactions within the neutrinos? Or you have 3+1, but then let's say you have a large potential ascribed to the fourth flavor.
Okay, so if there is some way that you have a new interaction and this term is increased, then you will suppress oscillations. Okay, so you
Okay,
will
so
suppress
that will tend to suppress the ineffective?
Yes.
Okay,
Okay.
thank you.
Okay. I think one case when you have a large lepton asymmetry can be suppressed, if I remember well. But it must be very large.
Here.
Okay, same reply. Wait. Just for recording.
Yeah, can I just naively summarize that the existence of extra neutrino whose mass is below like MeV is not preferred by the cosmological data of like
Which mass is less than?
is not preferred by the cosmological data of N effective. Can I say that?
Yes.
Yeah. So
Let's say I will say that it will is
so in that
strongly
case,
disfavor.
so either there should be some extra interactions as she asked, and or like the mass of neutrino should be like larger than 1 MeV, so that it's not contributing radiation energy density.
Yes. Okay.
Gotcha.
What I'm not sure, and I wanted to ask Maria yesterday, that what will be the bound, including DESI results on this case, 3+1, with fully thermalized neutrino? No, I know, but did you show yesterday that you have a limit on the effective number of neutrinos? So lambda Calder matter plus N effective, and a limit on the mass. But what if instead of what will be the limit on the mass, but with an effective equal 4?
Okay, but fitting with an NF
Mm.
equal 4 will be a very bad fit.
I know.
So, okay, the bound on the mass from new experiments, from new cosmological surveys is not really degenerate with the
With an
NF anymore. It was for
It
Planck, but it's not the case anymore. So it's not really, for instance, with Euclid, it's not really changing the sensitivity to the mass if you include a fourth sterile neutrino.
Okay.
So it should not change.
Ninetta.
But concerning the last point, actually, when the Planck or other experiment give the constraint on effective mass, they give always the joint constraint on an effective and the mass. So usually we never had the case, at least actually only 10 years ago with the double map and so on, but the recent data, N effective with the effective mass is always less than 4. Usually we have a 3.4 for an effective with a joint constraint on the effective mass. So
Okay.
actually with the N effective 4 is very, very difficult to accommodate. And my question is, I missed the difference between the two ternary plot you show. I mean,
You mean the
the last
difference
two,
between
yes,
these
yes,
two?
yes.
The mass.
Ah, okay,
You
okay.
see, that's the point. If the small, I mean, if delta square is small enough, it's okay. And effective will be 3.
But actually, I mean, is not in the direction of anomalies.
No,
So,
not at all. This will be in the direction of anomalies. You see the
Okay,
difference.
Thanks.
Sergio.
Okay, just one, I would like to ask you, okay, I see that from laboratory, the number of effective neutrino goes from 3.04308 So I want to have a better grasp on how sure we are in this discrimination, especially the small range of variation.
Okay, let me see if I understand well. The question is that, so I go back to this case, for instance, non-standard parameters, and you have two different non-standard parameters. This one here, this one here. The white bands are the constraint from laboratory experiments, not cosmology.
Yeah,
Okay, so you see that it's not that we can use the whole range. What is true is that when these laboratory measurements are published, they are always done in one parameter at the same time, maximum two as far, maybe only one. Okay, so there is no combine. Okay, so this is, we are showing that if you see, for instance, this case is still okay, this will be the effective number of neutrinos for cosmology. Okay.
Okay.
Sergio.
So I just want to understand, it's coming back to Georgia's question. So the reason why you get an n-effective below the standard value when you add the non-standard interactions is because you suppress oscillations of the NUE state, the NUME and neutral states into the NUE. So you suppress that via
You mean, for instance, this case?
Yeah.
No, because if you take this value of the epsilon and you add it to the standard case here, so you must combine these two Lagrangians, okay? So actually, for these values of the epsilon parameter, you are reducing the interaction. Okay?
You mean the cross section?
Yes.
So it's not because you are affecting the matter potential?
No, it's because you're reducing the interaction.
Okay.
You can actually do the calculation, adding these two and you
Yeah.
ELs and whatever, and for some particular cases.
So you have some cancellation in the amplitudes.
Yes, that's it. It's not really fully calculated, but it's
okay.
I also had a comment to the question, and then Maria. First of all, I wanted to ask you a precision concerning this because you had a previous work in 2005 on non-standard interactions, right?
Which I'm sorry.
2005, I think it was.
This paper.
This is 2021, no?
Yes.
There was a previous one, for example, on the effect of non-standard interactions.
Yes.
And I wanted to ask you a precision. What's the main difference? Because I think that also was three flavor.
Yes.
So what's the main improvement?
The main improvement is that we revise everything. We include all the possible effects. The computation is better. We can use, you see, more bin modes and everything. It is true that the results are not much different, but I think this is a better calculation. We can compare with this. For instance, we did some calculation, I think in 15 with a few cases, and I think comparing with this, it was not much different.
Okay, so still an improvement. And the other was a comment concerning the asymmetries. I just wanted to mention, you said the most recent, but Jérôme Gavard, who was my PhD student, and I worked on the neutrino asymmetries in presence of CP violation for the first time in a full three-flavor framework, but considering the damping approximation for the collision term.
Okay.
And that was in 2010.
Okay, I remember this.
So some time ago. Maria?
So if we really manage to get a sensitivity to an F point very small, then how can we tell if it's non-standard interaction or if it's a boson decoupling? There is no way.
We can't.
We can't.
No.
Right.
It can be one or the other. That's I don't think we can. But okay, but it's in any of these two cases, it's interesting. That's true. It's non-standard. Stefano, want a comment?
Can you go to the plot with the contour of the NSIs?
Yes. Which one?
Yes, this one, either of these. We cannot even tell if 3.044 is due to, let's say, epsilon tau tau equal to 0 or 0.5.
Or a combination of other parameters.
On all the ellipses, you have combinations that give the same n effective, and we cannot really distinguish them.
That was Francesco.
Sergio, the same plot, can you remind what are the constraints from lab, I guess, on epsilon? I mean, this constraint that you emphasize.
Yes, so I actually have a full table at the BN. Let me show you. Yes, these ones. Okay, so it's tight constraints on most of the parameters, maybe except for, you see, these ones here, which are still not all the one, but okay.
For instance, I mean, Camio-Grande, Borexino, super Camio-Grande, Borexino measurement of this elastic scattering on neutrino, are them relevant?
Actually, I don't know. Maybe. For my really remember is that the ones linked to the mu neutrino, you see, the bounds are really very tight. It's order of magnitude better than, for instance, these ones. But these I don't know. We can check it.
Thank you.
Julia?
Just to comment on the distinguish between different like bosons or whatever in N-effective, I guess the only thing would be BBN because I expect different scenarios would change the NUI spectrum differently, but we would need, I guess, precisions that we really don't have for now. And aside from that, just had a question. It's related to the question before. The main effect due to these non-standard interactions, it's purely from the collision term, or is it also the matter effect that is changed in a weird way?
Basically collision.
Okay.
Yeah. It's also because the effect of oscillations is very small.
Other comments or questions? Okay, if not, let us thank